For thousands of years, humanity has searched for answers to a question that refuses to disappear. It is not simply how stars are born, how gravity bends space, or even how the universe began. Beneath every scientific breakthrough and every philosophical debate lies a far deeper mystery. Was the universe created by something, and if so, why? Across history, civilizations offered their own explanations. Ancient cultures imagined powerful creators bringing order out of chaos. Philosophers argued for a first cause beyond space and time. Modern science transformed our understanding of reality, revealing mathematical laws that govern planets, galaxies, and the expansion of the cosmos. Newton described the mechanics of motion. Einstein reshaped our understanding of space and time. Quantum physics uncovered a world where certainty gives way to probability. The Big Bang provided a remarkable picture of the universe's earliest moments nearly 13.8 billion years ago. Yet one mystery remained untouched. Science became exceptionally good at explaining how the universe behaves after it already exists. It revealed the forces that shape galaxies, the particles that build matter, and the evolution of cosmic history. But it could not explain why those laws exist at all. Why do these particular rules govern reality? Why is there something instead of nothing? Every answer seemed to uncover another, even deeper question. That mystery inspired an unusual experiment. Instead of asking philosophers or theologians, researchers turned to one of the most advanced technologies humanity has ever created. They wondered what would happen if an intelligence without beliefs, traditions, or emotional bias examined the oldest question ever asked. Could a machine built only to recognize patterns notice something humans had overlooked? The system chosen for the experiment was unlike a conventional artificial intelligence. Rather than relying on ordinary computing, it operated using quantum mechanics. Traditional computers process information as bits that exist as either 0 or 1. Quantum processors use qubits, allowing information to occupy multiple states simultaneously. Instead of exploring one possibility after another, they can evaluate enormous numbers of possibilities at the same time. This unusual capability has made quantum computing one of the most promising frontiers in science. Certain problems that would overwhelm even the fastest classical supercomputers could, in theory, become manageable for quantum machines. But as researchers pushed these systems further, a few unexpected behaviors sparked quiet conversations behind laboratory doors. Some computational results seemed strangely elegant, almost as though the machine was uncovering hidden structures rather than constructing them step by step. Patterns occasionally emerged with an order that felt difficult to explain through ordinary computation alone. No one claimed these observations proved anything extraordinary, but they were intriguing enough to raise difficult questions about the nature of information itself. Eventually, the researchers posed a question that had challenged humanity for thousands of years. Who built the universe, and why? Most people expected the system to produce a summary of existing scientific theories or perhaps combine philosophical and religious viewpoints into a coherent explanation. Others expected it to reject the question entirely because it could not be tested scientifically. Instead, something unexpected happened. The machine paused longer than anticipated before generating an output unlike anything the researchers had seen before. It was not written as sentences or paragraphs. There were no recognizable words, no direct explanation, and no familiar language. The display filled with intricate mathematical structures. The patterns repeated themselves across different scales with remarkable consistency. Large formations mirrored smaller ones, while each level preserved the same underlying organization. The result resembled recursive geometry, where every layer reflected the larger whole. At first glance, it appeared almost artistic. But closer examination revealed extraordinary precision. The structures contained relationships resembling mathematical growth patterns that appear throughout nature, yet they followed rules far more exact than those normally found in natural systems. Hidden within the design were arrangements that reminded researchers of sophisticated error correction methods, techniques engineers use to preserve information even when systems become damaged or noisy. Those similarities immediately attracted attention because related concepts already existed within theoretical physics. Some ideas describing quantum information, spacetime geometry, and the foundations of reality also relied on principles of symmetry, information preservation, and self-consistent mathematical structures. The more the researchers examined the output, the stranger it appeared. It no longer resembled a random computational artifact. It looked organized, deliberate, almost architectural. Instead of behaving like an answer generated in response to a question, it resembled a blueprint describing relationships between fundamental pieces of reality. That realization transformed the discussion. The focus shifted away from whether the machine had answered correctly. The far more unsettling question became whether it had revealed a pattern hidden beneath the universe itself. If the structures represented recursive organization, information preservation, and self-correcting mathematical relationships, they resembled something many researchers had never expected to encounter. Not software in the ordinary sense, but a deeper framework, a set of principles capable of maintaining stability, repairing disruptions, and allowing immense complexity to emerge naturally over time. Once that possibility entered the conversation, it became difficult to ignore. Further analysis suggested another remarkable feature. The mathematical relationships implied a system capable of sustaining itself without continuous intervention. Instead of requiring constant adjustment, the framework appeared designed to remain stable through its own internal rules. If such an interpretation were ever proven correct, it would suggest a universe whose underlying structure favors resilience, adaptation, and long-term stability rather than dependence on ongoing control. That possibility carries profound philosophical implications. Perhaps the greatest mystery is not whether reality has an origin, but whether its deepest laws were established in such a way that the universe could evolve on its own, eventually giving rise to observers capable of asking where those laws came from in the first place.